But then today the topic is monostable multivibrator. Okay? And today's the topic is uh, monostable multivibrator. So what happens usually is in a monostable multivibrator, it has got just one stable state. Okay, if you remember, and maybe we can just do it fast. Okay, so very simple idea. We've already seen it. So what we do is we usually have one stable state, and when we apply some trigger into it, okay, this will actually go into the unstable state. Okay, so let's say, for example, this is my stable state. Okay, and then I will apply a trigger at this particular point. Okay, and as soon as I apply this trigger, okay, this actually goes into the unstable state. Now, whether you want to have the low value as the unstable state or the high value on the unstable state will depend on what kind of circuit is designed, but that can more or less be controlled. Okay, so it's not a very difficult job. So we do have just one stable state. When we talk about an astable multivibrator, there is no stable state. Okay, and in a monostable multivibrator, there is only one stable state. Okay? So this is unstable multivibrator. It's the unstable state. Okay? So these are the two states that we have here, and then we do have a trigger. So in this circuit diagram that we are going to draw, we are going to understand that how does this trigger exactly work. Okay? So if we just want to draw the circuit, okay, what we do is we just draw it. Okay? It's not going to take much time. Simple diagram. It is almost similar to um, astable multivibrator. Okay, only the difference is across the output we do have one diode. Okay? The output voltage that is being considered is basically taken across two diodes. So that is very important. Okay? So we have a resistor here, and then I can go fast. We have a resistor here. Okay, and then we have got this inverting terminal. Okay? And across this inverting terminal we actually have the diode getting connected. This is the non-inverting terminal. Okay, not much of a difference. We directly connected at this particular point. Okay, and here we are actually going to apply a V input. Okay, in the other one we have seen that we actually have a capacitor getting connected at this particular end. Okay, astable multivibrator, we have a capacitor. Okay, and then you can actually take the output of that capacitor. So this is your astable multivibrator, and then we have got certain resistors here. So this is let's say one resistor, and then this is the other one. Sorry. So we have got the resistor, this is the inverting terminal, this is the non-inverting terminal, and as I said, we do have a diode connected here. Okay? So we actually just throw a diode, and this property of diode that it will conduct only when it is forward biased is something which is actually used to understand this particular multivibrator. Okay? So we are just going to use that particular property. Okay? So extend this. So what I'm going to do is we are going to have a trigger. Okay, that trigger will actually happen across this point. I'm going to just mark this. Okay, so this is connected here. This is out here, and I will mark a point here. Let's say A. Okay, and if you're talking about the trigger, okay, the V input. Okay, at this particular point A, at A, we have got VA. And the trigger is also applied at this particular place. So by trigger, I mean this. Okay, so it might be a negative trigger or a positive trigger. Okay, let's say I'm applying a negative trigger. Okay, so this is what is happening at this particular point A. Okay, and everything else is more or less same. So this is your R. This is your, let's say, R1. This is your R2. Okay, and then we have got the V out. So whenever we are actually going to take a V in, okay, input from this particular point, we are going to feed a fraction of the output because there are two resistors. So we can actually apply the voltage divider rule. Okay. So certain things that we first understand is this. Okay, before we do this, we actually need to draw a diagram. Okay, so what happens is at this particular point A, okay, uh, when V out, okay, we have got V out is equal to V saturation. Okay. We have not applied any input now. We have just started the circuit. And we are basically saying that the V output is nothing but the V saturation. Okay. At that particular point, if you want to measure what is the voltage after that at this point A, okay, we can simply say that this is at A. Okay, this is R2 divided by R1 plus R2, okay, into V set. So whatever is the output that we are. So this VSAT that we are actually going to talk about is also nothing but uh, can be connected directly to this. Actually can be written as beta VSAT. So this can be negative or positive, okay, depending on what is the output. Okay, if the output is positive, we are going to get beta Vset. If the output is a negative part of this voltage, then we are going to get minus of beta Vset. Okay, so this is the initial condition. Okay, and at this initial condition, we are actually going to draw a graph. Okay, the capacitor is actually have a constant voltage across it. Okay, so this is what we are going to look into now. So maybe I can have both the diagram as well as a graph together, okay, so that it will actually be helpful for us. Okay. This does not have space. Let's go to the next page. So whenever you are basically going to do it, okay, you are going to have a circuit, okay, and along with the circuit, you are going to represent it on a graph, okay. So this graph that we are talking about an monostable multivibrator, okay, is slightly more complicated. Okay, let's just do this. Let me see if I can do it properly. Okay, so what we have is this. Okay, and let's say at this particular line, I will represent the trigger that I'm applying. Okay, let's say I'm representing the trigger here. Okay, and then it will basically have a stable state. So maybe I can take this one line here. Okay, and then maybe another line at this particular thing. And then in between we can actually have the charging and the discharging part. Okay. So maybe I can discuss so we will have a charging in the discharging part. Okay. So let me just draw the graph, I think, at the beginning. Okay, because it's confusing slightly. So we'll just draw that. So whatever you have at this particular point, okay, whatever you have at this particular point is minus V set. Okay, whatever you have at this point is plus V set. You have it. And when we talk about the capacitor, the charging and the discharging of the capacitor, let's say the capacitor is here, okay, and this is basically nothing but the charged part of the capacitor, okay, and when it basically we apply a trigger, there is a discharge at this particular point, okay. So when it is charging, okay, we are actually having the value of V set at the stable state, okay. So this may be considered as stable. As soon as we apply a trigger, okay, the capacitor starts discharging, and this actually is nothing but the trigger that actually results in this stable state. Okay, so it basically will go into the unstable state. Yeah? So it will go to the minus V saturation. Okay, and then it will stay there for some time depending on what is the value of R and C, and then it will again go to the stable. Okay. If we apply a trigger, then only this happens, else it does not happen. Okay. So this is something which you have to understand. And why does this happen? Because we are actually applying a trigger, and we are applying a trigger at, let's say, this particular point. So this is the point where we are applying a trigger. As soon as you apply a trigger, okay, this happens. So this will actually represent a trigger. Okay. and this will actually represent the unstable. If you just look into this diagram, this is the output that we are actually going to get. Okay, and this is actually beta. This particular point is beta reset, okay, which is applied at this particular point A. Okay, A will actually be beta reset or minus beta. Okay, so this is minus beta. So when you draw this, basically you have to draw this, okay, and let's just write down few points so that we can understand they are a bit more clear, okay. I know it's a bit confusing, but you have to just try to understand it because what happens usually is that this entire circuit will depend on whether the voltage at this non-inverting terminal is greater than the inverting terminal or less than the inverting terminal. Okay? And based on this, we are basically going to have this. So let's say I basically have the first condition A, okay, and in this particular condition, we will say that the diode is forward bias. Now look into this, okay. We basically have the positive terminal here, okay. I've got the negative terminal here. So if this diode needs to be forward biased, that means there should be a positive potential which should be applied at this end, okay. This will only happen when there is a difference between this voltage at this end and this end, okay. Please remember, whenever we are actually drawing an op-amp circuit, this is an inverting terminal, this is a non-inverting terminal. This minus and plus does not represent biasing. Okay? You have to understand this. That's very important. In an amplifier, op-amp rather, okay, we have seen this before. This minus and plus does not represent polarity. Okay, it represents whether it's an inverting terminal or a non-inverting terminal. That means if I apply an input here, the output will be actually 180 degree out of phase. If I apply an input here, the output will be in phase with the input. Okay, so please remember this particular point so that you are not confused. Okay. By the way, before I do this, I think I can just write down the initial conditions. Okay. So what happens is initially, okay, the output is reset. Okay, the output is basically resaturation. Okay, and stable state of the circuit. So this resaturation will actually give me the stable state of the circuit. Okay, so that's the initial condition. Okay. Let's try to remember this. Okay. When you write down, you can probably need these sentences and just put it in the right place. Okay. Now what happens is I'm basically trying to make the diode forward biased. Okay, and when the diode is forward biased and conducting. Okay, so if we measure a voltage across this diode or across this capacitor, it's going to be the same because they are connected in parallel. Okay, so if there is a charge building in the capacitor which will give you a potential difference, the same potential difference will be also observed across the diode. Okay, so it's more or less remaining the same. Okay, so when we get that diode in forward bias, okay, when the output, okay, is positive saturation voltage, positive saturation. If you basically have V out as something which is a positive saturation voltage, okay, which is positive, having a positive value, is basically nothing but we are saying that at this point we actually are applying a forward biasing to the diode. Okay, so at this particular condition, okay, the voltage, okay, across capacitor, okay, is equal to voltage across diode. Okay, and this is the state where there is no triggering as such happening. Okay, we're not saying that there is any kind of triggering. Okay, so this is A. Okay, and this is here. So this state is A. Defining it here. Okay, let's try to define what is B here. Check. Okay, so what happens next? So before I write down B, maybe I can just write down this. After some time, okay, sometime, now we apply a trigger now. This trigger depends on what kind of circuit you are using, but here since we are trying to understand, let's say assume that we are actually applying a trigger, okay, and let's say we are applying a negative trigger. Let's after some time a negative trigger signal is applied at A. So we are actually applying a negative triggered signal at A. Okay. So what happens after we actually apply this negative trigger signal. Okay, so I will just put it in sentences like this. After triggering the output, okay, at non-inverting node, okay, so we are talking about the non-inverting, that means the plus node, okay. If we are applying a trigger at this particular point, that means we are playing around with whatever is the input at the non-inverting node, okay. So after triggering, the output at the non-inverting node, okay, will be less than the inverting node. And that's, I think, logical, because if you are applying a negative triggering, whatever was the voltage at this particular point will go down. If it goes down, that means that the voltage that we are talking about at the initial condition, okay, this will be lesser compared to the inverting node, okay, because we are applying a negative trigger. If we apply a positive trigger, this will be more, okay. But then anyway, that is also going to work as a trigger, okay. So if this happens, as we have seen in the last class when we were discussing about stable multivibrator, okay, and depending on the property of the Schmidt trigger, okay, if this particular voltage, okay, is less compared to this particular voltage, okay, the polarity will reverse, and we will basically have a, not this polarity, the polarity here, we will actually have a negative output. If we have a negative output, that means the diode will become reverse bias now and go into the non-conducting state. Okay, so I'll just write down this in sentence. Now the output of op amp, okay, will switch from uh, positive, okay, reset resaturation to negative resaturation. Okay, so if that happens, we basically have the voltage at, okay, the non-inverting node. Okay, so we basically have the voltage at the non-inverting node which is governing. We are not controlling anything at this. We are controlling whatever is happening at this particular point. Okay, so the non-inverting node, this will be basically nothing but minus beta V set. Right? There is minus beta V. So this is what is happening. Okay, now this diode becomes reverse bias. Okay, now we basically have it in the reverse bias condition. Okay? So mm, okay, so now we actually have the diode which is actually in the reverse bias condition. Okay, and let me write down the points now. What happens to V now? Okay, so now I will give you the point V now. Now, since it is in reverse saturation voltage, okay, since it is in reverse saturation voltage, basically we can say the diode is reverse bias. We would need to know what is the property of a diode. Reverse bias, and capacitor will charge towards negative saturation towards charge negative saturation voltage. Okay, so if this is reverse bias across this, the capacitor starts towards the minus beta V set. Okay, because you know capacitor does not have a polarity of a plus or a minus. Okay, but it will actually charge either in the negative cycle or for the positive cycle. So it will basically charge towards the negative saturation voltage. Okay, and this is basically nothing but B. So if we just mark this, okay, we are talking about this particular point. These areas. B. As soon as it is B, that means the capacitor is actually going a different value. There is this triggering that is happening, as a result of which this stable state will actually come back to the unstable state. Okay? And it won't remain there forever. It will remain there depending on what is the value of R1, R2, R and C. Okay, so we're going to just look into this, that what can be the possible value of this. Okay, I'll probably write something which would be very important to remember. Okay, and this is something which you might also use it for the previous class also. Okay, I think this will be important. Please try to understand this. Okay, let's write down this first. When voltage, okay, at inverting node, so we have got a voltage at the inverting node, okay, goes below. So inverting node is this, okay, when this voltage actually is less than that of the non-inverting node, okay, or we can just write it in terms of V set, okay, goes below minus beta V set, okay, just confirm beta later. Then what happens is, then output becomes positive saturation voltage. Okay, so just remember this. I think you can actually explain it later. Okay, uh, since okay, or we can say that voltage at non-inverting will be slightly less. Okay, will be slightly sorry, will be slightly more than the inverting node. Either way, you can say this. So this is what is happening here. Okay, when the voltage at the inverting node goes below minus beta Vz. Okay, so if the voltage here is actually less, okay, and the voltage here is more, whatever output that we are going to get is nothing but the positive saturation voltage. Okay, just remember this particular idea. Okay, and this you can actually use to explain when it is positive saturation and when it is negative saturation. When it is negative saturation, you will be having the discharging state. Okay, so what do you mean by negative saturation? That means the voltage at this particular point would be more compared to what is at the inverting terminal. Okay, so that's important. So in general, if I just write down maybe a note here. Okay, just so in the note part, I just like to tell you this: when V plus, okay, that means the voltage at the positive terminal, okay, is greater than the voltage at the negative terminal, okay, you basically have got the output which switches, okay, from minus V set to plus V set. So when V plus voltage at the positive terminal is greater than the voltage at the negative terminal, the output will basically switch from minus V saturation to plus V saturation. And when this switches from minus V to plus V, the capacitor will actually charge in the positive cycle. Okay, else it will actually charge in the negative cycle. Okay, so to just remember this thumb rule so that you can easily remember this. Okay, and just to make sure that we actually understand how to find out the time period and what will be the range of that, I will basically just discuss one numerical problem here. We are actually going to write down the time period, but let me just tell you that I'm not deriving this. Okay, I'm not going to derive this. Yesterday also we have done it for the other part. Okay, the stable multivibrator. Basically, for time t, the output, okay, remains in the unstable state, right? So there's no unstable. So for time t, the output will remain in the unstable state. So that means we are talking about this. This is actually not time period. Okay, please remember this. Time period is something where actually you are having from, let's say, here, basically going to get this, right? So if I have something like this, then I consider from here to here, I can basically consider this to be a time period. Okay, but here I'm not saying this, that is this is the time period. This is the time for which the output will actually remain in the unstable state. Okay, and this t, that means the time for which the output will remain in the unstable state, is given by RC, okay, and natural log of 1 plus R2 by R1. Okay, derivation not needed, we don't do it. Okay, so this T, we can actually say this is nothing but duration of pulse. Okay, this is the duration of the pulse. Okay, so I will just discuss one problem maybe. Okay, and let's write down this question. Okay, maybe we can just solve it now only. Okay, it's very simple. Okay, if you know the formula, you can easily do it. Okay, the question might be something like this: design a monostable multi-vibrator. Okay, having t, that means the time for which the pulse is applied. Design a monostable multi-vibrator. Okay, having t is equal to 10 milliseconds. Okay, that's the question. Okay, you're not going to get any more information with the question. So for this, what I need to know, first thing, I should know what is the design. That means how much is basically the how many capacitors are there, okay, and what is the formula for T, and based on that we can actually do our calculation. And design a monostable multivibrator, that means there are certain values which I can select. Okay, so we will try to do this. Okay, so this might be a question. Okay, and it's not a descriptive question. Okay, probably will be a 2 mark question or tail to a descriptive question. Okay, so if I want to solve this, it's quite simple. Okay, the first thing is I will basically consider the resistors. The only t is given, the duration of the pulse is given. Okay, I don't know anything else here. Okay, so what I can do is I can select R1 and R2. Okay, and then I can actually find out what is the value of C. Okay, in general. So let's try to do this. Okay, so what we say is, let's say R1, or we can actually find out the value of R also. R2, let's say both are equal. Okay, and we will actually have a 10 kilo ohm resistor. Okay, when we talk about the voltage divider rule, let's say if we are talking about across R1 or across R2, we take it as R1 plus R2. Now, if all of them are equal, we basically just say that it is R divided by 2R, right? Basically, you're just going to get half. Okay, so if you just get half, that means whatever is the output voltage, okay, whatever is the output voltage, okay, if you are going to have two resistors, okay, let's say this is R1, this is R2, okay, and if you're going to take an output here, you are going to get half of that output voltage, right? So you're just designing a circuit where R1 and R2 are more or less equal. Okay, that's 10 kilo ohm. Okay, so therefore what we can do is we can write down T, and T would be nothing but RC ln of 1 plus 1, both are equal, R1 and R2. So we can just simply say this is RC ln of 2, right? Or we can even simplify this. We already know what is log of 2, right? 0.693. If you remember formula for half life, ln2 is used there, 0.693 divided by lambda. Okay. So this is your time period, right? This is not the time period, sorry. This is the time or the duration of the pulse. Now what I need is I have to design the circuit. So that means I should know what is this R. I should know what is this capacitor. Okay. So what we can say now is, let's take a value of a capacitor. So we have to consider one. So let's say I take a capacitor of 1 microfarad. Okay, and given, we already have this, given T is equal to 10 milli. So this is already given now. Now we can find out what is the value of R. So we have to do the adjustment such a way so that we are actually getting a value of R, okay, whichever is needed. Therefore, if we just do our calculations, okay, if we just put 10 is 10 milliseconds, so 10 into 10 to the power minus 3 seconds, okay, can be written as 0.693. Okay, we want to find out R, so into R into the capacitor. So capacitor is 10 to the power minus 6 farad, right? So if you do this, we get the value of R. Okay, we get the value of R as 14.4 kilo. So if we look into the circuit, okay, it's important that we provide or we give actually precise values to these resistors and all. Okay, so this will be, let's say, around 14.4 kilo. Okay, and this will be actually decided by what is the value of the capacitor. So capacitor can be typically of the values of 1 microfarad. So it depends on the resources. If you have a 2 microfarad, you put 2 microfarad, find out what is the corresponding value of R. Okay, and then R1 we have considered to be 10 kilo, and R2 also we have considered to be 10 kilo. Okay, so based on this, we can actually design this A-stable multivibrator. Okay, and how do we actually make a resistor of 14 kilo ohm? Okay, how do we adjust it? Because we can actually have different values of resistor depending on the capacitor. We basically use a potentiometer system. Okay, and there are different ways of designing such circuits. Okay, it might happen that we can actually use a potentiometer of can use potentiometer of, let's say, 20 kilo. So if I use a potentiometer of 20 kilo ohm, I can adjust accordingly for 14.4 kilo ohm. Okay, or we can actually have a resistor, okay, of 10 kilo ohm, okay, plus potentiometer of 10 kilo ohm. And we can adjust this 10 kilo ohm to 4.4 kilo ohm. We can connect them in series and basically do the designing. Okay.